So hopefully you know what the picture is there. That is a pulley. So when we exert force with just a string, all the force is kind of being wrapped up in that string. And when we then insert a pulley, we now have direction of force that changes. Basically what the pulley is doing is you have force being pulled down, yet on the other side the force is coming up, right? And so it kind of spreads out the force, so to speak. If you've ever had to lift anything, the difference between lifting something with a pulley and just lifting it's completely different, right? It does reduce the workload of lifting things. And so when we start to think about pulleys, we are going to start to think, well, if this is my positive direction for this one, then that's my positive direction for the other one. So it kind of flips the way you think on some of these, because you're actually acting opposite of what you want. If I want to lift something and it's on a pulley, just a simple pulley, I'm going to pull down to lift up. And so we're going to start looking at those, just like the tension was opposite, you're also going to look at the movement as opposite as you look at these pulley systems. And so just like when we talked about the free body diagrams and we had ideal strings, we actually have ideal pulleys, because pulleys are going to change the force. Now, we're going to see systems where they're hanging. We're going to see systems where one is sitting on a table and the other one's hanging. And so we're going to look at different ways that these work, but it changes the force. And we're going to talk about how it changes the force. All right. So the first thing is when you're transmitting force around a corner, the direction of the tension in a string can be changed by using a pulley. So we do employ ideal pulleys. When we're doing these scenarios, we're thinking of an ideal pulley. And so we're going to talk about that a little bit, but we're talking about how the direction is changing. They are also thinking ideal strings. Remember what we talked about. Those aren't going to stretch. We're going to consider mass and those things that have to do with the string itself. And so as you're pulling it this way, you have another tension that's going that direction. And so we're going around a corner, so to speak. So what is an ideal pulley? On an ideal pulley, the wheel and the axle are both massless and frictionless, okay? We will introduce friction right now, but most of your problems that you're going to see are either going to use the word ideal in the problem, or the instructions are going to say, assume that you have ideal string and an ideal pulley. By that, they mean we're not consider the mass of the pulley, and we're not going to consider any friction on the pulley. The motion around that wheel is also frictionless. So again, we're going to consider that it is not causing any friction on the string itself or on whatever you're using to pull it up. And honestly, the other thing you have to think about, granted, in real life, when you use a pulley, you have to maintain it. And yes, it can cause friction if something's going on. But if you were to try to pull that string over and over like the corner of a box, you're going to wear it down a lot more than when it's just rolling on that pulley, right? And so the idea of an ideal pulley is that it's just freely going around it and that you don't have that catch that happens. All right. The other piece is the pulley changes the direction of the tension in the string without diminishing its magnitude. Remember, magnitude is how much force, in this case, we're putting on it. So the pulley itself is not going to diminish the magnitude at all. All right, so let's look at an example with a pulley. All right. So it says a 3.5 kilogram mass and a 4.75 kilogram mass are connected by an ideal string over an ideal pulley. What is the acceleration of the two-block system? What is the tension in the string? All right. So just like our free body diagrams that we drew with the single string holding the boxes like we just did, you are going to consider the fact that you have one tension working one direction and one tension working the other direction. So we are going to go right back to Newton's laws here, all right? We're going to go right back to the sum of the forces equals the mass times the acceleration, all right? Now, what are the forces working on these two boxes? So you may or may not be able to see, but this first box here, this is going to be our 3.5. The second box here is going to be our 4.75. So we're going to deal with the first box and then the second box, and then we're going to set them equal just like we did before. All right. So this first box has two forces acting on it. What do you think one of the forces is? Gravity. It's gravity. So we have the force of gravity working on it. And then the other force is going to be that ideal string. Okay? It is going to equal the mass of that times the acceleration. So then what is the force of gravity? Well, it's what the force of gravity always is. On this box, the force of gravity is going to be 3.5. In fact, I'm going to wait and fill this in. I'm going to move this over so you can see the little formula that we're going to keep using over and over. Tension is going to then equal the mass times acceleration minus the force of gravity, right? Which is what we just saw. So the tension then is going to be this mass, which is 3.5, times an acceleration that we do not know, minus the 3.5, times the negative 9.81. The pulleys are a little bit different. So when we're talking about pulleys, remember I said that one's going to be going up while the other is going down. And so if I look at this particular one, and on the left-hand side, I say, well, this direction is going to be negative for this guy, and that direction is going to be positive, all right? Let's say I chose that. You can choose one. It's fine. But once you choose it, the other guy is going to be opposite, okay? Which means for the other one, his positive is going to be the other direction. So this is going to be his positive, and that's going to be his negative. All right? They are working inversely of each other. Okay? They're working inversely of each other. It's similar to the tension that we talked about, but now we're even going to think about it with movement, okay? Meaning, when I set this second guy up, which we're about to do, then I am going to, yes, I'm going to negate that tension. The tension is going to be pulling the opposite. So I'm going to look right back at this same thing that I did right here, and I'm going to set him up for the second one, all right? His tension, however, is going to be the opposite of the other one. He's still going to have mass times acceleration minus the force of gravity, all right? That's what his is going to look like. His tension is going to be opposite. This gravity on this box is still pulling towards Earth, correct? Yes? But what is that direction for this guy? Positive or negative? There we go. So when I plug in, I'm still going to say, and yes, as her question, we will move that negative over. His tension is going to be negative mass times acceleration, 4.75, times an A that we don't know, right? Minus mass and times gravity, all right? So mass, but now gravity is moving it in its positive direction. Gravity is moving it in its positive direction. Now, if you had set it up the other way and said, no, I want the bigger box to be going positive up and negative down, then the other box would be positive down and negative up, right? It doesn't matter which way you set them up as long as you know that they are working opposite of each other. Because if the bigger box goes down, what's going to happen to the smaller box? It's going to go up, right? If the smaller box goes down, what's going to happen to the bigger box? It's going to go up. So once you set the parameters for your coordinate system here, once you decide, okay, I want this to be negative and that to be positive for him, you must flip it for this guy. Does everybody see why? It's a pulley. It's reversing. It's reversing the movement. So that's why on this one, I did negative 9.81 when I talked about gravity, because that was moving it in this direction. But over here, I did positive 9.81. It's still moving it in this direction, but for this guy, that's its positive direction. Any questions on that one? So when we do that, we have our tensions now. We have set this negative tension. We've distributed that negative. It equals T. We have this equal to T. What can we do with them? They both equal the same thing. What can we do? Set them equal to each other, which is exactly what we're going to do. So we're going to say the 3.50. Go ahead and multiply this out. Your negative 3.5 and your negative 9.81. We will worry about significant digits at the end. We're going to distribute this negative. So I have negative 4.75a. Distribute it here and go ahead and multiply. Make sure that you get those numbers. So the question was, is it going to be positive or negative? Yes, it is, right? It just depends on how you set this up. The way that I set it up, let's see what makes sense. All right, let's see what makes sense here. Positive. What's the positive movement on this little guy right here? Up, right? Yeah, that's the way he's probably moving, right? What's the positive acceleration movement on this guy? Down, probably the way that he is moving as well, right? Does that make sense? And so this is why they're opposite, because the acceleration of the entire system is the same, meaning he is accelerating up just as quickly as this larger one is accelerating down. So had we gotten negative acceleration, we probably would have gotten negative acceleration if we switched these two, meaning that if we had said this was positive for him and negative for him, right? And positive and negative, then we would have gotten a negative acceleration here, which again would mean the little box was moving up and the big box was moving down.
So it just depends on...
How then do I solve tension? Well, they equal each other. So I can either plug it into this side or plug it into this side and get my tension, because they each represent the same thing. They both represent that tension on that string. So go ahead and calculate tension. You can solve it on either side of that equation. This is analyzing a system with pulleys again, but this one is a little bit different, right? It says we have a 1.5 kilogram block resting on a frictionless table. It's attached to a 1 kilogram hanging block by an ideal string passing over an ideal pulley. It's mounted to the table's edge. What is the acceleration of the two block system? What is the tension on the string? All right, so here's the thing. We have a couple things to think about for this one. First, let's talk about this larger box here. This is my 1.5 kilogram, all right? He is sitting on the table. That's what it just told me, right? So if I look at the vertical force on this, it is equal. He is not falling through the table. He is not floating above the table, right? So that means the force that the table is putting on the block and the force the gravity is pushing down on the block must be equal, right? So we have no force up and down, really. Some of that force is zero. They zero each other out, okay? What we do have is we have a force that's moving this direction for him, all right? So his sum of the forces is really only moving to the right, supposedly, if he's moving at all, okay? So for this particular one, his sum of the forces is going to be his mass times acceleration, as it always is. However, the only force acting on this in that direction is the tension. That's the only force acting on him that way. We don't have anyone pulling that block. That's the only thing acting on the block. It's going this direction and it's tension. That's the only force, all right? We know his mass, right? His mass was given to us, 1.5. We do not know his acceleration. So that's the tension there. It's your mass times acceleration, all right? This particular one right here, so he's a little bit different. He has a couple of forces acting on him, right? First of all, he has the tension. Now remember, we'll get to that, but his tension is going to negate. So we'll just put his tension for right now. But he has gravity acting on him because he is hanging. He has force pulling him down called gravity. So the force of gravity plus he has tension that's pulling him that way. So his force has multiple things affecting it, right? His sum of the forces. That will again equal his mass, which we know as 1.00, times the acceleration that we do not yet know. All right, and I'm going to put this as t prime so that you know that that's his tension pulling up the other direction. All right, so if I were to solve for his, I would say his tension equals the 1.00 minus the force of gravity. That's going to be his mass times, we're going to use gravity going down here. Mass times acceleration. And because these, remember, are working opposite of each other, if I want to replace it with that, I need to put a negative t there, right? Which means I need to distribute a negative through to all of that goodness, all right? Now again, it depends on how you set up the positives and negatives here. If you have this as the positive movement and that is the negative movement, you would have put a positive 9.81 there. It all depends on how you've set this up, right? We just know that the other box is not moving up or down at all. So if I distribute that, I have a negative 1.00a, and I'm going to minus the 9.81. Now I have my two tensions equal to each other. I've already distributed that negative, and I can solve. So I'm going to set my two tensions equal to each other, just like I did before. 1.50a equals negative 1.00a minus 9.81. What is my acceleration? What is my acceleration? Go ahead and solve for it. Depending on how you set up your positives and negatives, you would get 3.924, significant digits, 3.92. You may have gotten a negative there, right? So if we use gravity going down as negative, you would get that as you would get. So if I were going to take that and calculate my tension, I would go back to this equation right here. That's the easiest one to do. Just plug it in. 1.5 times your acceleration. And you get a tension of, if you had negative again, it depends on your direction, it's going to look like that. we have systems that happen in inclines. And so when you think about an incline, again, just like when we did the pulley system and we were like, well, I'm going to decide that this is up and that's down, or positive and that's negative, or that this is positive and that's negative, the coordinate system is chosen. The coordinate system is chosen, and this will make a little more sense when we see the example, but you have a natural force. That natural force is always going to be perpendicular to this extended force of gravity here. You'll see that it's labeled G of Y, and that's because that's the gravitational force pulling directly perpendicular to the object. And then you have this force G, gravity. That's the gravity in the X position there, the horizontal pull. So when we think about natural force, it's just going straight up from the object. Gravity, however, is always going straight down and not in reference to the object, in reference to the earth, okay? So the object could be tilted, but your gravity is going to be straight down. It's not going to be perpendicular to that object, right? So what we do and how we get these is we're breaking down our gravity into X and Y coordinates pretty much, right? Just like we did before. You do have to consider your SOHCAHTOA situation, because before we always set it up so that our X was cosine and our Y was sine, right? That doesn't always work out with these. It depends on how you draw your sketch, all right? So the coordinate system is chosen. So this particular one says, I want X to be this way and I want Y to be that way. The only thing that you have to set for sure is that X and Y are perpendicular to each other. The X-axis is perpendicular to the Y-axis, which hopefully you know that way back from middle school math, right? But you can use any convenient choice to draw what that means to you. So it's always important that you draw it, because I do not know what it means to you unless you sketch it, right? Unless you can visually see and I can visually see what you mean by X and what you mean by Y. So let's look at the term normal force, which is what I was talking about with that force going upward. It's exerted by a surface on an object in contact with it. The normal force is always perpendicular to the surface, all right? So whatever is sitting on my desk, right? Let's say I have this stack of sticky notes and it's sitting on my desk. The normal force is going to be perpendicular to what it's sitting on, all right? If I have something sitting on something that is slanted, the normal force is going to be perpendicular to what it's sitting on, all right? Because the normal force means it is applying a force to this book, right? The book is applying a force back up, all right? That's what they mean by normal force. So it's going to be perpendicular to whatever it's sitting on, the surface that it's sitting on. That's your normal force. So when we analyze the systems here, the force of gravity always pulls things down. They have this boulder sitting. You can see the force of gravity right here is pulling it straight down. In this diagram, F of G is the boulder's weight, equivalent to the boulder force with gravity. The normal force then for this picture goes straight up from that, because this particular boulder is sitting perfectly flat. All right, so my normal force is the surface that that boulder is sitting on is pushing back. Per Newton's laws, right, that they are going to be equivalent forces. They're going to balance each other out. There's an equal and opposite force there. That's our normal force. Here, I have a direct up and down from gravity, right? But what happens then when it's sloped is you create these angles, all right? So now my gravity is still, you'll notice, straight down in reference to the earth or whatever object is pulling the gravity. If you're sitting on Mars, it's going to be straight down to Mars, right? We have this normal force that's going to be perpendicular to the boulder's position here. All right, so the boulder sitting on this slant, the normal force is no longer directly opposite of gravity. It's directly opposite of what it is sitting on, directly perpendicular to what it's sitting on. So it exerts a force on the ground equal to the magnitude of the component of its weight that is perpendicular to the incline. The normal force decreases accordingly. So when it's just sitting flat, your normal force is going to match whatever the force in newtons of the object, or the weight of the object, right? Your normal force and the weight of the object are going to be the same. When it's flat right here, The normal force on this is whatever the weight of this guy is, all right? But when you incline, that changes. And you can see it because on this, it doesn't move, right? But when I do this, clearly the force that's pushing back up is not enough to keep that where it needs to be because we have other things acting on it. We have gravity that's pulling in a different direction than what this thing is sitting on. And if the gravity force is bigger than the force that's holding it there, it's going to move, right? And so that's what we're looking at here. So let's look at how we calculate then what's happening to these. Normal force. Well, normal force is now going to be affected by this incline. So I'm going to sketch a couple things because this is the picture they gave me. So if I were doing a free body diagram, I want to actually draw out these vectors, all right? So I have this block. It is sitting on an incline. So notice some keywords here. 30 degrees, obviously, on a frictionless incline. Right now, we're not adding friction. We will. The block weighs 50 newtons, which is 5.097 kilograms. What is the normal force on the block? What is the acceleration of the block? All right. So let's look at some of the forces that are acting on this particular thing. The normal force then is going to be perpendicular right here. My normal force is going to go this direction. It's the force of this incline pushing back up on that block. We have the force of gravity. The force of gravity is right there. What we're going to do is we're going to draw a right triangle compared to that force of gravity. The force of gravity is going to be my hypotenuse of this right triangle. And so I am going to break this gravity down into an X and Y component compared to that slant. So I'm going to break it down here. That is going to be my Y component. And it's that way because it's going directly down from the surface. So this is my force of the gravity Y position compared to the surface. And then I have a force of gravity that is X to the surface. So I've really just broken down my gravity into XY components, all right? Because compared to the incline, it is not directly down. Over here, I do not have a direct up and down from gravity, from the incline, okay? So I have this right triangle that's created by the components of this particular triangle. Now, so what they're asking is, well, what is the force, the natural force then? Well, the natural force, based on Newton's laws, should match this force right here, right? Whatever force is pushing this direction, the natural force should be equivalent, but just opposite signs, right? So that's what we're going to do. We're going to break this down into components, So we're going to do this using something very familiar. It's SOHCAHTOA. Now, remember, I said it's not always X component is cosine and Y component is sine for these. All right, so we're going to talk a little geometry. Let's see how much we remember. This is a 30-degree angle. If I were to create a right triangle right here that went all the way here, that means this is 90. What is this angle right here? This angle right here. What is he must be? 60. Must be 60. 30, 60, 90. It's just because they all add up to 180, right? So that has to be 60, right? Does that make sense? If that is 60, this is called a vertical angle. So now we're looking at, pay attention to what I'm drawing because I'm going to show you the Y. I'm going to look at this little tiny triangle right there. That's going to be a similar triangle is what it is. That little tiny triangle, and I'll blow it up for you. So this is 30. That one must be 60 because of our 30, 60, 90, 180. This is 60. This guy is also 60. Does anybody remember why those two are both 60 degrees? Why would those two both be 60 degrees? Do y'all remember that rule in geometry?
They're like opposite.
Yeah, so it's vertical angles is what they're called. Vertical angles are always congruent. These are always congruent angles. So that means if this is 60, this guy is 60. And once again, I have a 30, 60, 90 triangle. Does everybody see that?
So what is this? Why is this important? Well, this is important because that means that the angle that is created from your y component directly opposite of your natural and your gravity is always going to match him. Geometry, all right? Because you'll always be able to walk to that. So the angle of the incline will always match this angle that is formed between the gravitational pull directly opposite your natural force, directly perpendicular, and your natural gravitational force. This angle and this angle will always be the same. Everybody see that? That's why that's important, because we must then use that information to calculate some things. If then, and I'm going to grab this triangle and pull him out a little bit. All right, so we're going to look at just him for a second. I need to calculate this guy right here because he's going to be the opposite force to the one they're asking about. They're asking about my natural force here. I need to find the guy that's opposite of him because they'll be the same, right? Equal and opposite. Well, what is this in SOHCAHTOA world, right? I know this angle measure, that's 30. I know this angle measure, that's 60. I have to find it. So in this case, they're going to always use the 30 because that's what was given to them, right? We know that the angle of the incline and that angle is going to match. So they're always going to use 30, but I need to find this. It says y, but according to this angle, this is the adjacent side, right? And this is the hypotenuse. Which trig function deals with adjacent and hypotenuse in SOHCAHTOA? Cosine does, right? And so when I want to find then that particular side, if it will let me grab just him, no, it's not, because it's going to be, because I wrote on it. If I want to find then just, oh my goodness, y'all, hang on, let me get him out of the, yeah, so 43.30 is pulling down, which means the natural force pulling directly opposite that is just the positive. 43, and because our smallest measurement is 3 significant digits, we're going to use 43.3. 43.3. That is going to be positive because they're asking about the natural force. This force, assuming that down is negative and up is positive, right? You have to apply that negative. It's not going to naturally give it to you just multiplying it by the cosine of that angle. All right? You will always have acute angles. Why will you always have acute angles here? Let's see. What was the normal force on this when this box was sitting on a flat surface? What's the normal weight in newtons of this box? 50, right? What happened when we inclined it? What happened to the apparent weight of this box based on that? What happened to it? It went down, right? It went down. That's why it's going to slide, okay? Because it went down. And so if there's a force that's not as much as what's happening to it, it's going to move potentially, right? Depending on how much force is going on. And so it makes sense that it would seem to weigh less on an incline if you're pushing down. So if you're pushing a box and you're pushing it straight across the floor, is that different than when it's on an incline and you're pushing it down an incline? Probably, right? It should be easier to push it down an incline than straight across, right? Because the force that's on it, the natural force that's on it is lighter at that point because you have an incline that's helping you. It's breaking down those components. All right, so normal force is going to be opposite of that y piece, but acceleration is going to be going up and down this particular incline, right? Which means it's going to be the x movement. We're trying to now figure out, well, what's happening this direction? We already figured out what's happening that direction, what's happening this direction. So now, in order to calculate acceleration, we are going to use our force equals mass times acceleration, but for the x piece, all right? Now remember, In the way that we drew it, our x piece is technically our sine. So to find our x piece of this, we're going to say, well, the force of gravity in the x position is going to be that 50 times the sine of 30, all right? 50 times the sine of 30. Sine is one that hopefully you know, that's 1/2, so this is just going to be 25. It is in the negative direction, because if you look at this particular plane here, if I have my xy coordinate that I have placed like this, right? This is my x, this is my y, this is negative y, this would be negative x. So if it's going down that incline, it's going in the negative direction, right? Gravity is pulling it down. Gravity is pulling it down. So this is the force that is on that particular object going down the incline. Force equals mass times acceleration. They gave you the weight of the object and the mass of the object. So they gave you the weight of the object. That's what we used here to calculate force. We're going to have to use the mass of the object to calculate acceleration. All right? So now we're just going to plug those in. Mass times acceleration equals my force. So we know two of those. What is the acceleration then on this particular box? What is the acceleration on the box? Calculate it. So you should have gotten that your acceleration, which is the second question here, is negative 4.90 meters per second squared. All right. So then the question is, what does that tell you about the box? What does it tell you about the box? What's happening to that box? Looking at this picture, what does that acceleration tell you about the box? Talk about measured weight. The scale exerts an upward force that balances the object's weight. That's how scales work. All right? In an unaccelerated reference frame and on a horizontal surface, the normal force is equal in magnitude and opposite in direction to the weight of the object. What does all that mean? It means that if I take something and weigh it, all right, and this is just common sense. If you are weighing something on a scale, are you going to hold it while you weigh it? Like if I'm holding this, what you probably can't see is that as I move this, the weight on this changes, right? In order to accurately weigh something, they're going to say, well, you need to set it down, right? On a flat surface, if you've ever looked at what a scale tells you to do, put it on a flat surface, and then you want to weigh it, right? Then you want to set it down and weigh it. I'll weigh this because he's not heavy enough. All right, so when I set it on a flat surface, this says this weighs, let's change my units to grams, 123 grams, right? That's what that means. A scale naturally pushes up as whatever you're putting on it pushes down, all right? Unaccelerated on a horizontal surface, meaning I am not moving this horizontal surface, then whatever it's reading, whatever it's pushing up, is going to be equal to how it's pushing down, all right? That's what we've been doing the whole time. The boulder sitting flat on the ground, normal force pushing up, same as force pushing down. It's not moving, it's just sitting there, all right? What we found was when we inclined it, it changed it. It changed that normal force, right? What also happens is when you move it, it's going to change apparent weight. So measured weight is just whatever the guy weighs. That's what he weighs. So if we determine the weight then, remember weight includes direction. So weight is technically asking for force. Does that make sense? So it says a 25 kilogram crate rests on a scale as shown. The display shows the magnitude of the normal force on the scale on the crate. The crate and the scale are at rest. What weight does the scale indicate? What weight does the scale indicate? Well, all they did was they gave us the mass. If they're asking for weight, they're asking for force, right? Does that make sense? If they're asking for weight, they're asking for force. So if I want to calculate the force here, the only force acting on this object right now is gravity, right? Gravity compared to its mass. And so I'm going to say, well, the force that's showing should be the mass times the acceleration. Now, you can use a negative here. I will tell you, your scale is never going to say negative, right? That would not make sense in our brains. So we can just assume that it's going to be a negative because it's pulling down. What you'll also notice is this little guy that I said you may want to draw, right? The weight or the force of gravity is going to be negative here, but which one are they asking about? They're asking about what the scale is going to say. The scale is the natural force, the normal force pulling back up. So even though you use gravity, negative 9.81, the natural force is going to be the opposite of gravity, which is going to do that. Does that make sense? So when you're calculating just straight flat, you can ignore the positive and negative of gravity because we're going to do the opposite, right? We're going to do the opposite. However, when we start pulling this with a moving object, you're going to have to think about the fact that gravity is going down. So when you multiply this out, what do you get? What do you get? What is the scale going to show you here? 245. What did we just get it in? 245 newtons. All right, newtons. 245 newtons. Apparent weight changes with a change in acceleration. All right? If I take this scale and I have this block of pads and it is sitting on my scale, it's going to give me one thing. But if I take this scale and move it up and down, it's going to show something different. Why? Because my scale is moving as well. So normally it would just be saying pull of gravity, right? But now we have another force. This guy itself is moving. And so all of a sudden he has a pull that is affecting the acceleration of that pull. We have multiple accelerations going on, right? If I'm going down, we have an additional acceleration in line with that gravity. If I'm going up, we have a different acceleration in line with that gravity. And so we have something happening. Did the weight of this change? Well, no, the weight did not change. The apparent weight did, though. It seemed as though it had changed, and even the scale would read it differently. All right, and so that's what it means by it changes in acceleration. So, it says a physics is doing an experiment in a school's elevator. She places a 10 kilogram box that weighs 98.1 newtons, and they've kind of said, hey, here's the force of gravity, 98.1 on a scale in the elevator. The elevator is accelerating upward with a uniform acceleration of 2 meters per second squared. What weight does the scale indicate? All right, so all of a sudden, these are moving opposite directions, right? I have one going this direction, and I have another going that direction. They're working against each other. So I am going to take the mass of that object. I'm trying to find the force here, right? I'm going to take the mass of that object, but now I'm going to multiply it by that 2 that is going up, and I have to subtract that gravity that is pulling down. They're working against each other, right? So I'm going to take the 2 going up, and I'm going to subtract the force of gravity. I'm going to subtract the force of gravity. So all of a sudden, instead of 10 kilograms, that would normally be 98.1 newtons. What is that force going to show now when I multiply it? Well, when I multiply that out, it's going to show 118 newtons. Did the 10 kilogram box change mass? No, the 10 kilogram box did not change mass, right? But what did change is my acceleration, all right? My acceleration changed. And so what happens when I go up with this guy is these numbers go up. Because all of a sudden the force getting pushed against him is more than the force that he's pushing down, right? And so when your scale is balanced, this should show exactly the force that's pushing down. It's not doing anything. But all of a sudden when I start moving him up, he has force going up more than the force that was originally going up. Natural force is going to be balanced. Natural force is going to be the same force, right? But when I move this elevator up, it's pushing up more than, which means the scale is going to naturally read more. All right? And so it looks like it's weighing more, but it never changed weight. It never actually changed weight. The acceleration of what was happening to this changed, right? So then what happens... here's what they're telling you. If A is in the opposite direction of gravity, you're going to subtract those two. You're going to take whatever the acceleration is, and you're going to subtract the force of gravity because they're going opposite, right? It looks like the weight's more than when the object was just sitting still. So then what do you think happens when the elevator goes down? What do you think happens to the weight, apparent weight of it? It also goes down. Why is that? Well, when it is just perfectly still, we're just equal. Whatever he's pushing down, the weight of the scale is going to push right back up and say, here's what I'm pushing up at, right? But all of a sudden when I drop it, it's not pushing up as much, right? All of a sudden this is going down and it's not pushing up as much as it was. And so on the scale, it's going to look like we have less weight when we don't. So then we're going to take this again, and they're working together, and we're going to do the same thing. We're going to subtract those two, but all of a sudden you're going to see that this is less than the 9.81, whereas before it was more than the 9.81. And so it will look like that 98.1 Newton will now read 78.1 Newtons. Since the object's acceleration is in the same direction, this makes the apparent weight less than when it's at rest. So then what do you think would happen at free fall? Free fall, they're both falling. They're both just free falling. What do you think the weight would be on the scale? What happens is your acceleration of your elevator, hopefully you're never in an elevator that is free falling, but you will feel like you weigh nothing. That's the good news, right? If it is free falling, what you're in is falling at negative 9.81 meters per second. You are also pushing down, right, because of the gravitational pull at 9.81 meters per second. And when you combine those, we have that 10 grams. We have a negative 9.81 minus a negative 9.81. In all math, when you take a number and subtract itself, you get 0. And in all math, when you multiply by 0, you get 0. It would seem as though it weighed nothing. So if I were to take this, I won't because I'll probably break my scale, and just drop it, the scale would read 0. It would read 0 because they're both falling at the same rate. So the scale is not able to push any force up at all. It's falling. This is just what we said before, right? It appears weightless. This is actually what happens when you look at astronauts. Which is that last couple pieces here. That astronauts and satellite in orbit are free fall, are still affected by gravity. It only appears that they are weightless.